Okay, in the previous section, we learned about condensation of a aldol reaction. So basically, aldol involve two carbonyl compounds, which could be the aldehyde or ketone, whereas a Claisen condensation is a condensation reaction of two molecules of esters. So this is two molecules of esters. Ester, this is the ester functional group, carbonyl group with oxygen attached to another alkyl group. So if you have two molecules of these in the presence of a base such as ethoxide, and then the second step you're adding hydrochloric acid, we're going to form a beta keto ester. So here you have a ester. Okay, so this is the ester functional group, and if we label them as our alpha beta carbons, this is a alpha and this is a beta. So in the beta position we have a keto group, and this is a ester functional group, so we call it as a beta keto ester. Okay, the new bond is formed between the alpha carbon and the carbonyl carbon. That is exactly similar to what we had seen in the aldol reaction. Here also the new bond is being formed between alpha carbon of one of the molecules of ester and then the carbonyl carbon of the other molecule of the ester. It's the same pattern, but our starting materials are different. That's the only difference. Okay. The nucleophile should be identical to the alkoxy group of the ester. Now we have this ester group. So in this ester we have alkyl group, a methyl group, and we need to have a nucleophile, or the nucleophile also should be same as the O alkyl group. Otherwise, we would end up getting a different ester than what we started with. Because if you look at here, so you have an ester, you have a nucleophile methoxide. Methoxide can add onto the carbonyl carbon of the ester, and then you will have tetrahedral intermediate, and once it reforms the ester, it can lose any of these methoxy groups. But what happens if you use a different ethoxide? Let's say you different alkoxide. Let's say you use this one, CH3CH2O minus. This is ethoxide and the other one is methoxide. So you have this and you add it on to this carbonyl carbon. It's possible that this can happen in the reaction medium, and then you are going to form this molecule O minus. On one side you have OCH3, and then the other side you can have OCH2CH3. Now this is a reversible reaction and the ester want to reform back. So when it reforms, there are two choices. It can either lose the methoxy group or it can either lose ethoxy group. What happens if it loses the methoxy group? What is the ester you're going to get? You're going to get your ester as CH3CO or CH2 CH3. So you're going to be getting a different ester than what you started with. You see here the difference between these two. One has a methyl group and then the other one has ethyl group. So to avoid a confusion like that, when we are using ethoxide or a methoxide or an alkoxide, we want to make sure you use the same nucleophile as the OR group of the ester. Okay. Now this is the mechanism for the Claisen condensation. We need a nucleophile. It's going to be same as the alkoxide that we have in our ester group. So we use methoxide. It's first going to form the enolate. Now we are very familiar with that. So this is the alpha hydrogen. Methoxide will grab the alpha hydrogen from the ester and form the carbanion. This is stabilized, or it has a resonance stabilization with the enolate Okay, you know that. But the carbon ion then can go and add on to the carbonyl carbon of the other ester. Forms the four-membered intermediate, tetrahedral intermediate, because you're going to be forming a carbon-oxygen single bond. And then the carbonyl group need to reform back, and then it's going to lose the methoxy group from here. Okay, so this is going to be the end product. So you have ester from the one side, and then you have the carbonyl group from the other side. And then the methoxy group is lost. That is the mechanism for the Claisen condensation. So what do we make? What do we make by condensing two esters? So this is your carbonyl carbon. This is your alpha beta. So it's a beta keto ester. So in the beta position we have a keto group. So beta keto ester. Now if you are given a molecule like that and ask how do you synthesize this, then you know this is the alpha carbon of one of the ester. You can break this bond from here, and this carbonyl group come from the other ester like this. Okay, so we can also think about the reverse of this reaction too. Now the Claisen and Aldol addition. So let's look at the differences and the similarities of these. In the Claisen condensation, so you form a carbon-carbon bond between the alpha carbon of one of the carbonyl compound and then the carbonyl carbon of the other one. Same thing with the aldol. Alpha carbon of one aldehyde forms the bond with the carbonyl carbon of the other aldehyde. Similar way that they form the carbon-carbon bond. And then the formation of a pi bond by elimination of alkoxide. Now, once you form the new carbon-carbon bond in both cases, the next step for the Claisen is reform the carbon-oxygen pi bond by losing an alkoxide ion. And that will give you this carbonyl compound and then the rest of the molecule. What's going to happen to the aldol? Aldol does not have another group that can eliminate like alkoxide over here, but instead oxygen will protonate to give an alcohol. So we form beta hydroxyaldehyde in aldol addition, where in ester condensation we have a beta keto ester. Beta position you have a keto group. Here in the beta position you have alcohol group. Do you see that? But this is an ester, but this is an aldehyde. That's the other difference. Okay. A successful Claisen condensation requires an ester with two alpha hydrogens. Now here is an ester. So we are going to condense two esters. So you have alkyl group CH2, COOCH3. Two alpha hydrogens. So what are our alpha hydrogens? These are our alpha hydrogens. Now let's see, why do we need two alpha hydrogens? Now what's going to happen first when you add your base or a nucleophile methoxide, this will go and grab one of the alpha hydrogens, right? And then it's going to go ahead and condense with another molecule, and then the whole process take place that we had seen with the mechanism, and then you have this molecule which is the beta keto ester. One of the ester alpha carbon form a bond with the other ester carbonyl carbon. Okay, now this can form a beta keto ester anion, because you see here in this process, remember we are losing a methoxide ion. If you remember the process, you can see here, you see at the very end in this part over here, to form the keto functional group over here, the carbonyl group, you are losing a methoxide. Methoxide is a nucleophile. What are they good at? They are good at taking another acidic hydrogen, nucleophile as well as a base. Okay, so what it does is once the methoxide ion is formed, it's gonna go and grab this hydrogen and form methanol, and it forms a beta keto ester anion. Now, so that this one that we just formed, it is going to be resonance stabilized with the two carbonyl groups, giving added stability, and that propel the reaction forward to making this anion, because anion is going to be resonance stabilized. What if you don't have alpha hydrogen, another alpha hydrogen over here? So then it will not have that added stability. Okay, a second hydrogen is removed to prevent the reaction from reversing to the starting material. Okay, so once a second hydrogen, another reason is once a second hydrogen is lost like this, it would not go back to the starting material, because the resulting carbon ion is resonance stabilized with the two carbonyl groups. Obtaining one product from a cross Claisen. If only one carbonyl compound has alpha hydrogens. Let's say over here, this group carbonyl, and then the next carbon, alpha carbon, do we have any alpha hydrogens in the benzene ring? No, we don't, right? Because this is a there are 4 bonds on the carbon, so there are no hydrogens on this carbon, meaning there are no alpha hydrogens. Okay, so you're going to be reacting this with ethoxide. Remember, it has to be the same kind nucleophile as the alkyl group, so it's ethoxide. So you're going to be adding this one slowly. So you keep the base or the nucleophile in your reaction mixture, you add this one slowly. So when you're adding slowly, so this is going to go and deprotonate one of these alpha hydrogens and form the carbon ion. Okay, so once the carbon ion is being formed, this is going to react with the carbonyl compound of this one, instead of reacting with another molecule of this, because we are adding slowly, we have less concentration of this molecule in your reaction mixture, so it needs to go and react with this carbonyl group. Okay, that's why we follow this process. So form the new bond between the alpha carbon and then the carbonyl carbon of the other molecule. And then ethanol is the byproduct. The carbonyl compound with alpha hydrogens, which is this one, added slowly to a solution of the carbonyl compound without alpha hydrogens and a base. Now in this case, both carbonyl compounds have alpha hydrogens. So what do we do now? What we do is we use the molecule that we want to form the carbon ion, and we first react it with LDA. LDA is a strong base, it's going to go and take the alpha hydrogen and form the carbon ion. Once you already made the carbon ion in the reaction mixture, then you slowly add the other molecule. So then there is no time for this to make carbon ions. This is already been made. This is going to go and react with this carbonyl carbon and form the new bond. So this is the new compound. This part from this ester, OCH3 carbonyl group. This part over here, let me draw it or circle it. So this part is going to be this part. Just bend it, and this carbon ion reacting with this carbon over here, right? And then in the process this group lost, so carbonyl and methyl group. This part right here is this part. Once you understand what's happening and then understand the mechanism of it, it's not that hard. Okay, LDA is used to form the enolate ion and the other carbonyl compound added slowly. Cross condensation between a ketone and an ester. If, okay, only one carbonyl compound has alpha hydrogens. Now this is an ester. And this ester does not have any alpha hydrogens, because this hydrogen is not considered alpha hydrogens. Alpha hydrogens are on alpha carbons, and this one does not have any alpha carbons. Okay, this is ethyl formate, and our nucleophile going to be ethoxide, and we're going to be adding this one slowly. Since even if you have the nucleophile in the reaction mixture, there are no alpha hydrogens, nothing will happen. They just stay together. I mean, it can add here and then remove here, it doesn't matter, it's going to be the same product. Okay, and then you're going to be adding this one slowly. When you add this one slowly, what's going to happen? The ethoxide react with the alpha hydrogen here and form the enolate. Once the enolate is being formed here, or the carbanion, this is going to go and react with this carbonyl carbon. Okay, it will take this hydrogen and form the carbanion. Carbanion over here, and this is going to go and attack this carbonyl group, opens up, come back down, lose that. So what you are doing is you have this group, and then on this position you are adding this group. See? That's what happened. It can happen onto any side of this one, either here or the other part. So that's a beta-ketoaldehyde. The carbonyl compound with alpha hydrogens is added slowly to a solution of the carbonyl compound without alpha hydrogens and a base. It is kind of the same thing repeating, which is a good thing, so you don't have to worry about too many deviations. Okay. Cross condensation between a ketone and a diethyl carbonate. Ketone, this is our ketone, and this is a diethyl carbonate, meaning you have two alkoxy groups. Only one carbonyl compound has alpha hydrogen, which is this. Again, you have your nucleophile. Adding slowly, you form carbanion either here or here, and then once an ion forms, it's going to form a bond between this carbonyl carbon, and one of these groups would be lost. So then you end up with a beta keto ester, because only one group is losing. Okay, so that's a beta keto ester. The carbonyl compound with alpha hydrogens added slowly to a solution of the carbonyl compound without alpha hydrogens and a base. Okay, any questions? Okay then. Let's ignore this slide. Okay, summary of cross condensations. If both carbonyl compounds have alpha hydrogens, use LDA to form the desired enolate and then add the other compound slowly. If only one carbonyl compound has alpha hydrogens, the carbonyl compound with alpha hydrogens is added slowly to a solution of the carbonyl compound without alpha hydrogen and the base. Diekmann condensation. Well, Diekmann condensation is a cyclic ester formation. Let's talk about that here. Let's say you have this compound which is a diester. Now so far we had seen in the Claisen condensation, it is a condensation between two esters. Now do you see that the both esters in this one in the same molecule? So this is ester functional group, this is ester functional group. We call it as Diekmann because that's the name of the scientist who found it, but it is the two ester functional groups are on the same molecule. It's a 1,6-diester. And then we use the nucleophile methoxide. Now what's going to happen here? Again, so there are alpha carbons over here and here carrying alpha hydrogens. So it's going to form carbanion, and then it's going to go ahead and react with itself into the other carbonyl group, and then form the single bond, pi bond, and leave methoxide group. That's a beta keto ester. I think we have the mechanism in the next slide. So the Diekmann condensation is intramolecular Claisen condensation. So this is the mechanism for that. And here's a 1,7-diester. So here's a 1,6-diester. It forms a beta keto ester with 5-membered ring. If you start with 1,7-diester, you will end up getting a 6-membered ring, beta keto ester. Let's see the mechanism. So when you add methoxide, so we have alpha hydrogens in several places. So there are hydrogens over here, right? So then the methoxide come and grab the hydrogen, form carbanion. Carbanion react with the carbonyl group of the other ester molecule in the same other ester carbonyl group of the same molecule. And then you're going to form a bond between this carbon and carbonyl group. And if you count the number of carbons, that ring has 5 carbons. So it's going to be something like this. Okay, and then the next step is reforming the carbonyl compound. So methoxy group will be lost. And then we have this beta keto ester, Diekmann condensation. And similar to that, we can also have intramolecular aldol addition. So what we had seen in the Diekmann condensation is the intramolecular Claisen condensation. Similarly, we can have intramolecular aldol addition. Remember the aldol, which is the alpha carbon of one carbonyl group forming a bond with the carbonyl carbon of the other group, other aldehyde of the ketone compound. Excuse me. So here we have a 1,4-diketone. So for the 1,4-diketone, when you add a base, so these are your alpha carbon. So in fact, we have alpha carbon here, alpha carbon here, alpha carbon here, and alpha carbon there. Okay, so if the hydrogen on this carbon is get lost with the base, you form the carbanion, and intramolecular condensation take place, aldol addition in fact. So it's going to go to this carbonyl carbon. So if you count the number of bonds, so this is number 1. 1 is going to combine with, let's say, number 2, 3, 4, 5. So it's going to be a 5-membered ring. Okay. Or if I just number it from here, 1, 2, 3, 4, 5. So 5 is going to make a bond with 1. Okay, so this is going to be your number 1 carbon, number 1 right there. You can count, you can follow number 1, and 2 would be this, 3 would be this, and on the 4th position you have the carbonyl group, and 5 and 1 made the bond. Do you see that? And then when you add water, so this is going to grab the hydrogen from the water, and then it forms this product, one product form. Okay. Now remember I told you this is also alpha carbon. Now if the anion forms over here in this position, it's going to form a 3-membered ring, which is going to be highly unstable due to the ring strain. Ring strain is the bond angle is 60 degrees, so which is very, very strained molecule. So because of that, it's not going to form. Okay. So yeah, so that reaction will not take place. Two different enol ions can be formed. A 5-membered ring is favored over a 3-membered ring. Another intramolecular aldol. Now this is a 1,6 diketone. The previous one is 1,4 diketone. In the 1,6 also, you can see here, you can form the carbanion here, and if you do that, if this carbon and this carbonyl group forms a ring, that's going to be how many members in this ring? 1, 2, 3, 4, 5, 6, 7. Normally 7-membered rings also not that stable. Okay, two different enolates can be formed. A 5-membered is more favorable over 7-membered ring. 5 and 6 are the perfect ring structures. And even if you look at your cholesterol and any other steroid molecule which has many rings, you will see 5 and 6-membered rings are the more common ones because they are sterically more stable. The bond angles are perfect, and then some of the interactions that they're going to have, they are favorable over 4, 3 or 7-membered structures. Okay, so this one, the second one, if you form the carbanion here, if this alpha hydrogen is lost, carbanion would be formed here. So now we are making the bond between, if I number them 1, 2, 3, 4, 5. Okay, so the bond is going to form between 5 and 1. So this is going to be, I gave number 1 for that carbon, which is this one is number 1, 2, 3, 4, 5. 5 and 1 form the bond, and on the 5th position you have this handle, so you have that part over there. Okay, and then when you add water, it forms the product, beta hydroxy ketone. Another example of intramolecular aldol. When you have 1,5-diketone, there are so you can form the carbanion here and then form the bond here. So then you will have 1, 2, 3, 4, 5, 6-membered ring. So that's what in fact been formed, beta hydroxy ketone. Okay, how this is being formed? You form the anion here, and this attack this one. And if I number them 1, 2, 3, 4, 5, 6, 6-membered ring. And on number 1, that's going to be number 1, and then the 2, 3, 4, and on the 5th one you have a carbonyl group, and 6 and 1 made the connection. And with 1,7-diketone, excuse me, you will form carbanion over here. 1, 2, 3, 4, 5, 6, 7, 8, 8, 7, 6. This is 1, 2, 3, 4, 5, 6. 6 and 1 form the bond. And on the first carbon, number 1 carbon has this methyl group and then the OH, and number 6 carbon has this CO and CH3. Okay, we'll stop here.